All right, so my name is Shahid Barkat,
Joseph Kearney.
and we are the co-developers of AutoImpute, which is a package. And today we're going to be talking about all of the above, end-to-end. What is the challenge that we're trying to solve? Why? How we actually go about that through a four-step approach, and then really go into the AutoImpute package itself, speak to what it does, how it works, and then a demonstration of a specific use case of where you could actually use it. So what is the challenge? So what is the issue that we're trying to solve here? And kind of what Brad alluded to, it's like the bane of our existence. The first thing that we do in this slide, or in this beginning, is we're going to create a data set. So create a bunch of data points. We're going to create a data set containing X and Y variables, and then we're going to add missingness. And so we add 20% missingness in X, 30% missingness in Y, and then we show you a plot of that. So simply put, there is a bunch of data points, X, Y, in a plot. This shows some correlation and there's some missingness in this data. So the next step then is, for most of us, is okay, let's put this into a machine learning model, supervised machine learning model, and try to get prediction. And so we use scikit-learn, popular Python package, to do that, and we're gonna do a linear regression. X as a predictor, Y as a response variable, and let's see what happens. Well, it fails. It gives you an error, and the reason is because you have missing data, which all of us know. So any type of machine learning model that you do with scikit-learn is going to give you this error because you have missing values. So this was the fundamental premise that we worked off of, is what do you do now when you get in this scenario, when you have missingness? What do you do as a data engineer, data scientist? Well, you have to look at the whole pipeline. And so our package focuses on the end-to-end analysis of this pipeline, starting with the missing data itself. By exploring the missingness in a data set, you can actually understand how your missingness occurs. And then from there, at that point, you need to make a decision. And the two most common choices that people make are, well, I'm going to do list-wise deletion. I'm going to remove all the values that have missing observations, and therefore I'll have a full data set that I can run into my machine learning model and get predictions off of. Okay, valid option. Second option is do imputation. Imputation, as many of you know, is the process of filling in missing values with values using a variety of different tens and hundreds of different methods or algorithms that you could use for imputation. So one of the problems with that is, how do you choose which is the right one for your data set? And two, if you do choose one, how do you even understand what your imputation is actually doing to the data set? And then you take that and you put it into your linear regression, for example, and you get a prediction and a coefficient. You get a coefficient and you can use that for predictions. But what is actually happening? What is the effect of that decision that you made on your data set that's actually leading to this output? And so our package focuses on that piece, is the effect of imputation on a data set leading into analysis. And so is there a package? Yes, there is. AutoImpute is the package to do this. There are others as well, but this is the one that we built in Python, focused on the analysis end-to-end, the end-to-end analysis for this. And so we have a four-step approach. First is understand the missingness in your data. Step one always is what is going on in the data set and what does the missingness look like. The second step is then understand why that missingness actually occurred in the data set. And so there's something called the missing data mechanism that we'll speak into further in the background section. But basically understanding why that missingness occurred in your data set. The third is we're going to use our package to then try a bunch of different imputation methods to see what effect it has on the data set when you're filling in values using these methods. And then lastly, we're going to run that new data set, each one iterated, into a linear regression and see what is the output of that on the coefficients, the bias and the variance of the output that you get, and see the actual effect that it's having into the analytical model at the end. And so going into the background, what we first need to understand is the missing data mechanism. So there's three types of missing data mechanisms. The first is missing completely at random, MCAR. And the fundamental premise here is that MCAR is any time there is missingness with an equal probability of missingness. So no matter what's going on, the chance of being missing is equal. And so MCAR is a very strict condition, and most oftentimes in the real world, we don't see this, but this is the starting point is MCAR data sets. The second and less strict is missing at random, MAR. And this example is focused on the probability of a variable being missing based on the actual observed variables themselves. And it'll be easier when I go through the example of actually understanding what this means. But for now, just take my word for it. And then the last piece is missing not at random, which is now we're actually causing missingness in our data set that is actually the probability of it happening is based on the unobserved variables. So we have no idea what's actually causing that missingness, and therefore we need to model that missingness itself to really understand why it's not at random. And that is the reason there is this concept of ignorability, and that is the assumption that we will start with anytime we're doing any type of imputation, is that if we have a missing at random or missing completely at random data set, because it is based on either equal probability of missingness or the observed values, we can claim that they are ignorable, and therefore we can then impute them. Missing not at random, we would have to model the missingness to understand why it's missing, and therefore it becomes a much larger challenge. So for the sake of the scope of this conversation, we're only going to be focusing on missing completely at random, MCAR, and missing at random. So to show you an example of what this means, for example, everyone in this room, we were doing a weight loss contest, and the first step is we're going to get everyone's starting weight. Well, missing completely at random is everyone's getting on the scale, and randomly, for whatever reason, the battery dies. And we're no longer able to collect data for weights. And that isn't based on any other thing except the battery died. It's not based on, if you're tall or short or heavy or skinny. It's just because the battery died. Missing completely at random. Equal probability that it's going to be missing. The second is missing at random, which is that now your missingness is dependent on a known variable. And that known variable is whether or not the surface that we weighed you on was soft or hard. So anytime we weighed you on a hard surface, we got your data point, we got your weight. Anytime you were on a soft surface, we did not get your data point, you did not get your weight. And if we know that we measured you on a hard surface versus a soft surface, we could use that known variable then to actually impute those values. And therefore it's missing at random. And the last piece here is missing not at random, which is anyone who is over a certain weight, they were too heavy, we did not capture their data set, their data point or their weight. And because that scale just could not scale, right? So that's missing not at random. Entire group of people, because of an unobserved variable, is missing because of their weight is too heavy. So hopefully that makes sense, because this is the foundation of what we're going to talk about. All our examples are based on understanding missing completely at random and missing at random data sets.
So once we understand the mechanism for missingness, our next step is generally to pick a strategy to deal with that missingness. Now, the strategies we go over here have their pros and cons depending on the type of missingness that exists. But first, we'll just go into what those strategies are and how a process generally works to impute missing data. So as we mentioned earlier, the two general strategies are deletion and imputation, right? So deletion involves removing records from a data set that are missing and just discarding those rows altogether. That can often be fine if your sample size is large and the missingness in that sample size is relatively small. But if the amount of missing data starts to grow, you can't just start throwing out rows. That will lead to often a reduction in power for statistical models. It will lead to much larger standard errors in modeling because you're discarding important values in your data set. So what we focus on mainly in this is imputation. And imputation can come in many forms, right? So first to start, there can be univariate and multivariate imputation. Univariate imputation uses a feature or a vector itself and characteristics of that vector to impute missing values. So you could take, weight, for example, and you could take the mean of the weight and fill in anything that's missing with the mean of your sample. That would be univariate because you're not using any other features in your data set. Multivariate imputation would be using the other features such as age, such as the scale surface, right, to determine whether or not you use a specific value for weight as an imputation, right? Then once you've picked imputation strategies, the question is how many times should you do those imputations? And so the example here walks through starting with missing data, then doing single imputation where you impute missing values one time only, and then we show multiple imputation where you impute the same missing values multiple times, right? And so why we would do this might seem counterintuitive at first, but it's important to remember here that missing values themselves are unknown, right? So because they're unknown, we're not trying to find point estimates for them. We're not trying to find perfect values for them. We're trying to capture the fact that we don't know the true value, right? So multiple imputation helps us capture the variability when imputing values that we don't actually know, right? So here, in single imputation, 25 and 18, if we were to use those alone, right, we'd essentially be subbing in those values and saying that we're certain that these are the values for what was previously missing, right? So multiple imputation is the framework that allows us to impute the same variable multiple times. And in doing so, as we see later in the presentation, we can capture the variability between imputations and actually start to say things about the missingness itself. So if we look at this pipeline in regression, right, how would we do regression with multiple imputation? So we start with that same example, incomplete data, right? We perform multiple imputation using imputation methods, which we'll get to some examples later. After that, we run an analysis model, in this case linear regression, on each imputed data set separately, right? So we see here we actually end up with 3 models. One for each of the imputed data sets. Obviously, those models will be different because the imputations in each data set are different. And then the final goal is to pool those models in some way to give us one final model, right? And so that one final model will have coefficients, but it will also have additional metrics that can help us understand the variability between imputations and how certain we are about this coefficient, or how reliable we think it is, based on the variability in our imputations. So that is the pipeline that we've put forth to do regression using multiple imputation. And that should be, enough of the background information to kind of dig into the package. Before we do that, some considerations that we wanted to, put out there before going into a demo, before looking at the package, are these 4 bullet points, right? So it's important to understand the missing data mechanism and pick imputation methods based on that. What you're doing here, again, is not trying to find point estimates for missing values. You're not necessarily trying to predict things. What you're trying to do is preserve relationships in the data that you're imputing, right? So if you're imputing one variable, you want to preserve the variance, the distribution of that missing variable, or of the marginal distribution of that variable itself. You also want to preserve the covariance structure between imputed variables and variables that you might not be imputing. And again, in that, it's important to remember that imputation is not prediction. The last thing here to clarify that's not on this slide is this all is under the assumption of ignorability, right? So here we're assuming that the distributions that govern the observed data are the same that govern the missing data, right? And so that's why we want to essentially preserve those distributions and the covariance between features. If we actually had data that was MNAR, a lot of this would become a lot more complicated because the missing data itself might be governed by a separate distribution, right? So with that in mind, we can go into the package. So yes, its name is AutoImpute. Getting started, right? So obviously it's on the Python packaging index. You can pip install it. We designed it to be simple and familiar, right? So it follows the same API as scikit-learn, but it can also be very flexible, right? As we'll see in subsequent slides. You can get started very, very simply, or you can take control over the imputer and the regression models, right, to do a lot of custom and complex stuff. So the heart of this is really the multiple imputer. The MI linear regression model, as we saw a couple of slides ago, actually just uses a multiple imputer under the hood before pulling estimates and spitting out a final regression model. But looking at the multiple imputer itself, yes, so a few things I just mentioned, same design as scikit-learn. So, creating an instance of the multiple imputer class is pretty straightforward. All of the formal arguments have default values. When we print the imputer, we leverage the base estimator from scikit-learn to have a good representation of the class object, right? And then it also subclasses the transformer mixin. So the methods of the class should be familiar, right? Fit, transform, and fit, transform. And so it follows a very easy, an intuitive design so that you can start leveraging it as soon as possible. So one look at the formal arguments here, right? As we see in this example, there's default values for all of them. We'll get into more detail about what those are on the next slide when we show a more complex example of the multiple imputer. Does that look all right? So in this case, let's go through some of the arguments, right? So here we're basically customizing our multiple imputer, tailoring it to do what we want. So first, n, the number of imputation rounds you want to complete. The strategy argument allows you to specify the strategy you want to use for imputation, and you can specify that by column, right? So in this case, we have a salary column, and we want to use PMM, which is predictive mean matching. We have a gender column, and we might want to use binary logistic regression for that, right? So we can use different imputation methods for different columns. The predictors argument similarly allows you to specify which columns you want to use to impute specific variables, right? So here we see in strategy, salary, PMM, and the predictors, we want to use every other column, right? But for gender, we only want to use salary and education, right? So we can actually limit the predictors that we use to impute other variables. Impquargs is essentially another argument that lets you further customize the actual imputation methods themselves, right? So PMM is a hybrid method, between like Bayesian regression and KNN. And so with Bayesian methods in PyMC3, you can specify a number of arguments, right? So what you can actually do is put them in the impquargs and further customize the different strategies that you use, right? So you can change the number of neighbors for KNN from 5 to 10. And basically control what PMM does, what logistic regression does. And those models will all follow whatever the package or the strategy that we're using is, and we have that documented as well. The last two, the visit sequence is the way in which you impute columns. So by default, it's left to right, but you can also impute columns in different orders. And the last one, return list, here I set it equal to true, which means that all of the imputations will run right away. By default, that can actually lead to pretty expensive computation. So by default, it evaluates lazily and just returns a generator. But the point of showing this is that there's a lot that you can do with the multiple imputer besides just create a class instance. You can kind of customize it as you see fit for any situation. And this does handle categorical and continuous variables. Okay, so the main features, I won't go too much into this, but the point of this package is to be end-to-end, from exploring missingness, visualizing missingness, doing different imputation strategies, and actually doing regressions on multiply imputed data. For the demo, we're going, and these are all of the methods that our package currently supports. For the demo that we go into next, we're going to focus on 3 methods. And we're going to walk through the end-to-end example from imputation to regression with some visualization along the way that will hopefully bring a lot of the dry background kind of more into a practical example, right? So the 3 imputation methods we've chosen are mean imputation, linear regression imputation, and predictive mean matching. Okay, so now we will go into a demonstration where hopefully all of what we just said will be a little bit more practical.
Do you want to explain PMM real quick?
I'll do that.
Okay. All right. All right, so the demonstration we're going to do is going to focus on 2 separate data sets. The first one is going to be MCAR, missing completely at random. So what we've done here is we've created a data set that's 500 observations. We've then created correlation between 2 variables, x and y, of 0.7. And then we've artificially created missingness in the form of missing completely at random. And the missing variable in here is Y. So X is fully observed and Y is 40% missing. And so what we're basically doing is creating a data set that's missing completely at random, and only one variable has missingness, but the two variables are correlated at 0.7. And we're going to do exactly what Joe said. We're going to do 3 imputation methods to show you the difference that each one has on this data set: mean, least squares, and PMM. The second data set that we'll walk through is missing at random. So same idea, 500 observations that we created, 0.7 correlation, and we created artificial missingness, mimicking missing at random. And the key point here to understand is X is now the missing variable, 40%, and Y is fully observed. And you will see why that's the case. And then when we walk through the same 3 imputation methods to show you the difference between MCAR and MAR and how the missing data mechanism actually affects the imputation methods used to impute those data sets.
Yeah, I think one more point to make on that is that here the process, the code is exactly the same, right? What we're highlighting is that while the methods that we introduce, mean, least squares, and PMM work across any data set you give it, the results will be dramatically different, right? So missing data imputation is I think a cross between domain expertise, understanding why missing data might exist in your field, and then picking the strategies that best handle the type of missingness as well as the location of missingness, right? So missingness within an independent variable is different than missingness within a dependent variable, right? So that's kind of the point of this example, but the actual code, step by step, is exactly the same. Okay, so first we'll start with the missing completely at random example, right? So step 1 in our 4-step process was to visualize missingness itself, right? So our package has plots to do that, right? In this case, MCAR is a data frame, and we're passing it to the 2 different functions that plot missingness and help us understand missingness in our data set, right? So the one on the left, we see variable Y. Here the black bars represent the number of observed. So here we see that Y only has 284 observed, right? So roughly 40% of Y are missing relative to X. The plot on the right shows the locations of missingness within our data frame, right? So because in this case X is fully observed, right? That's why we get a black rectangle. The important part is on the right here with Y. The white bars represent missing rows or records, and we don't see any pattern in them, right? They are evenly distributed throughout the vector, and they have no relation to X, right? So if we saw, for example, more whiteness toward the bottom, we would know that the likelihood of missingness or the probability of being missing increases as the value of X increases, right? And so looking at this graph really helps us reason about whether we're dealing with MCAR or MAR, right? And we should also note that there is no formal test for MAR, right? So you have to kind of use inference, right? To some degree, right? And so starting with understanding your data and visualizing it in this way can help you be much more confident about the next step, which is handling that missing data via imputation or deletion, right?
And just to add, that's why we've been kind of harping on the missing data mechanism so much, is that it's critical to understand, and there is no formal method or statistical method to prove that a data set is missing completely at random, missing at random, or missing not at random, which is why you as the data engineer need to use your domain expertise and knowledge of your data set and visualizations like this to infer which one you think it is, and then work backwards based on the imputation method.
Cool. So the next step here, we start with mean imputation. We'll show a little more code on this slide and the next slide than subsequent slides, just to explain how they happen, right? But in this case, we've already done the imputation, right? And we're doing multiple imputation with each imputation. We have 5 rounds, right? So in that framework, we use mean as one example, least squares as another example, PMM as the final example. When we get to PMM, I'll go into it a little more. But mean observation is the simplest, or mean imputation is the simplest. each of the 5 rounds, we impute the mean of y, right? It's a univariate method. We don't use any other information in the data set. And as a result, every imputation is the same, right? So if we look at the left plot, there's no variability in y imp 1 to 5, right? They're all stacked on top of each other, right? And what we've done is, created 5 rounds of imputations that essentially, we could have done with 1, right? So the subsequent rounds with mean imputation don't add anything. And then we've also distorted the marginal distribution of y here because mean imputation, will shrink the variance, right? Given that we're just essentially imputing the mean. These 2 plots, right, are how we kind of visualize that. They're again native to the auto impute package, and they help us look at what imputation has done to the distribution of the imputed feature itself, right? The next plot here, the one on the left, helps us look at where the imputed values actually are, right? So again, with mean imputation, each round, the blue values are all of the observed, the red values are the imputed. We can see imputing the mean doesn't really add much to the data set itself. And then on the right, we can see the results of how mean imputation will distort the correlation between X and Y, and as a result will distort or bias any regression weights and standard error estimates. One thing to note here, which we'll see in the regression analysis, this is pooled standard error. So when we do multiple imputation, we need to take into account the variance that occurs between each imputation round, as well as normal standard error that occurs within a regular regression, right? So in this case, because the mean is just imputing the same value every single time, right? There's no additional variability, and a regression will be too confident, in its biased weight. So mean imputation is really not useful in practice, but it is a good starting point to understand the types of things that can arise when you don't pick imputation methods carefully. So least squares makes some improvements, right? So in mean, again, X is completely disregarding any relationship with Y. Least squares at least considers that relationship by imputing values based on the line of best fit between Y and X. In the case of MCAR, we'll see that mean imputation leads to an unbiased regression, right? Again, when Y itself, the dependent variable, is missing completely at random, then the model you're building to impute missing values will be the same as the model you actually use for a regression. So it won't actually bias the regression weight, but what it will do is inflate the correlation between the 2 variables, right? Because your imputations are along the line of best fit, right? So when you impute with linear regression, you're removing any noise, in those missing values and saying that they all lie along the line of best fit, right? So that will artificially inflate the correlation between Y and X. And in practice, this is still used, and it's dangerous because the results are going to look very good. But in fact, while that might be good for prediction, what you're doing is putting way too much confidence in a model and disregarding all of the variability that we think is important to consider. The next one is PMM. So PMM is, as I mentioned earlier, a hybrid method. What you're essentially doing is creating a Bayesian regression, right? And we also support Bayesian regression, where you basically sample from the predictive posterior distribution and use those to impute. Here, what you're doing is creating predictions, predicted values for imputation using a Bayesian regression model. Then you're taking those values and you're finding like the 5 or 10 nearest neighbors from within the observed values, of the feature, right? So essentially what you're doing is saying, okay, well, based on my prediction, what values that are already observed are kind of close to this, and you take those values and then you actually substitute those as the imputation, right? So the reason this is important is because, again, we consider, MCAR and MAR, right? So what you're basically doing is saying, where are the areas where missingness is the highest, right? What are the values around that area that are actually observed? Which ones can I pull from and just put those as the imputation, right? The important thing here with the graph on the left is this is the first method that actually introduces randomness between imputation methods. That's why we have 5 lines that don't stack on top of each other, right? And this is where we actually start to look at how well methods perform under certain conditions, right? So later on, we'll see an MAR example where PMM does a lot better. Here with MCAR, the missingness is all throughout the data set, right? So PMM can't really focus in on one area. It's constantly pulling different values from different areas and imputing, right? And in doing that, right, sometimes the distribution is better than it is in the next case. And we kind of see that with this graph on the left, right? So the first imputation for PMM focused on imputing a lot of values that ended up being lower. The other ones were, more thorough. But we'll see that, the graph on the right, PMM respects not only, the target variable that it's imputing, but also the relationship between that variable, and other variables in the data set, right? So in this case, what we show is that PMM out of these 3 does the best. And we kind of pull all of those different metrics that we had on the last slides, right, into a table here, and then show actual regression results. If we had imputed data using multiple imputation, and then pooled the different parameters into one final regression. So in this case, that first slide where we pool all of our different models on specific imputations, comes to fruition here, and we get one standard error coefficient, one regression weight, and then variance within and variance between. Variance between is between each imputation round. So we can see PMM is the only one that actually introduces any randomness. Okay, so next we'll go through an example of missing at random using.
Yeah, so the same data set that we had mentioned in the beginning, except in this case, Y is fully observed, X is 40% missing. So same code as Joe was mentioning in the first example, we're gonna run through the same exercise in the second example and show you the differences that we see. So in this, you see the exact same thing. Y is fully observed, X has around 40% missingness. The difference though, that you'll see in the right plot, and I think Joe alluded to this, was that you see that the white lines are more toward the bottom of the graph on the right side, on the right picture, which is basically saying that our missingness is more focused in areas where Y is higher. And that's why it's missing at random. So going back to my point in understanding and inferring which missing data mechanism it is, if you were to see something like this and you were trained to see something like this, you could see that because there's more white spaces at the bottom, this is missing at random versus the other graph that we saw was completely evenly distributed missingness. That's an important key point to know.
And because Y and X have a strong correlation here, if the value of Y is where there's, if higher values of Y lead to more missingness in X, then those imputed values should, for X should be higher as well, right? And that's one thing we'll see that, some of the models aren't able to do very well if they don't respect the pattern.
Yeah, so similar to the first graph, mean imputation, right? We see a big peak, but the key difference here that you'll notice is that mean is biased. And why that is, as Joe is alluding to, is that because more of our values in X were missing at the higher end of Y, we're losing out on those values in our mean calculation. So a perfect example is you had a data set between 1 to 10, and all your missingness was at the end. So you missed 8, 9, and 10. Well, 1 through 7, your mean is going to be around 3.5 versus a 5. And so our bias is actually moved forward and shifted. Sorry, our mean is shifted and therefore biased to the shorter end of the scale. And you see that in this graph where the mean is actually shifted left. And so not only do you get this big pipe, big peak, because of the mean imputation, but also it's shifting it and biasing it in missing at random. The second point, similar graph, we see that mean imputation does not do well because of obvious reasons. It doesn't take into account the correlation between X and Y, and therefore we have a single line of imputation around in X.
And if anyone's interested in the complicated, we can talk after about that.
Yeah, the standard error complication, we could talk after the session. But least squares, same idea. We have multiply imputed 5 times, but because it's the line of best fit, every one is going to be exactly the same. Therefore, we see them stacked on a single line, line of best fit. And yes, although it does better than mean imputation in maintaining that distribution, as we see in the next slide, it also is doing the same thing that we saw in missing completely at random, which is narrowing our imputations on the line of best fit. And because, again, on the right side here, we see that the higher values of X we're missing, we're not taking them into account, which is why our line of best fit in this diagram is actually off from where it should be in the data set. It's actually more higher peaked, it should be a little bit lower. And because that's the higher values of X that it's missing out on. And because linear regression only focuses on the observed data, it has no idea of the larger missing values that it's missing.
Right, so here's an example where the MCAR example had an unbiased coefficient, right? And applying that same example with different circumstances in the data leads to completely different results, in your imputation and then eventually in your analysis model.
And then same thing, PMM. Joe alluded to this as well. In missing completely at random, it was a little bit more varied, actually maybe a lot more varied in each imputation itself. But because the missingness in missing at random is focused in an area where Y is larger, it's better able to, in each imputation iteration, better able to track that and correctly impute. And therefore, each one of those lines is a little bit closer to each other. The variance between is closer. And as we see, there's a lot more red in the higher areas of missingness. Therefore, PMM is doing a better job of imputing the missingness at the higher end and also maintaining the distribution of the data set in between X and Y.
And, yeah, because we're short on time, right, I think one of the good things to note here, right, is we've seen the first two methods kind of degrade as things become a little bit more complicated. PMM of these three is the most robust to handle MCAR and MAR. And so if you're going to use something out of the bat, right, I would use PMM. It's actually the default for continuous variables in auto-impute for that exact reason. Some of the other methods can be useful in different areas. But one of the things that we note on these slides, right, is that, in none of these areas do we say best or do we rank them from, top to bottom, right? It's very dependent on, all of the different factors, right? And in some cases, PMM will do better. In some cases, it won't. And it really just depends on, all of these considerations that we've had and then what's important to you, right? So if all you care about is regression weights and you don't care about standard error, right? Then you might not necessarily need to use PMM for all use cases. It can be prohibitively expensive on larger data sets, right? So there's a lot of things to take into consideration. The method depends on a lot of factors.
That's why the key point here is to go through this 4-step approach. Understand the missingness in your data set. Then that will help you understand what type of missing data mechanism is at play here. And if it doesn't, then you can go through the imputation process and you'll very quickly see that certain imputation methods are really bad for certain data sets. And so that's why we're saying that we're not going to recommend from auto-impute the best imputation method. We're going to give you the tools so that you can do the analysis and use your best judgment because you have the domain expertise as well as the knowledge in your own data set. So go through the steps, understand the missingness, understand the missing data mechanism, try different imputation methods, run them through analytical models and really understand what's happening, and that way you can better make a decision on what's best for you. And so real quick, we wanted to jump into some of the content that we have.
Yeah, so there's, it's obviously on GitHub, and then we have a website.
Hold on.
So last thing, we have a website with a number of tutorials that have like extensive code to walk through and explain all the different features of the package. They probably do a better job than we can, out loud in 45 minutes. So, and then lastly, we have a lot of future work and, are actively looking for contributors. So if anyone's actually interested in getting involved, right, there's tons of additional methods. There's, doing this on larger data sets. There's integrating Dask and, NumPy arrays and other things like NumPy arrays and other things like that. So, that's pretty much it.
Yeah, so our kind of call to action here is go out there, pip install auto-impute, try it, let us know your feedback, good things, bad things, and we'd love to get information from you all. So thank you for the time.
Can you for this presentation and for creating this great package for everybody to take advantage of. This is a common problem. I know everyone's probably here faced, so we have some time for questions. We left this run a little bit long because there was really great content here. So maybe just a few questions now, and we could probably catch up with these guys at the breaks.
So more than about the package, this is probably a more general conceptual question. If the intention is to keep the distribution same with the imputation, how is that really different? It's not really changing the entropy if you were to just exclude those missing values. So if there is no change in entropy, there's no change in information. Like I'm trying to like figure out what's really the advantage of imputing in that case.
Yeah, and I think that's so a good point.
Repeat the question.
Oh, yeah. Sorry.
Yeah, so the question was, what is the actual value of imputing if by removing observations, there's no effect to the change of information the data set provides or the entropy of that data set?
Right, yeah, and so I think to start, right, in some cases, removing observations from the data set is actually the best method, right? In cases where you have extremely large data sets, it's MCAR and the amount of missingness is relatively small, then discarding that missingness likely won't affect your model. It's also much easier to just drop missing records, right? In cases where the missingness is MAR, right? If you drop missing records, you actually might be losing information. For example, if your missingness is all based off, like a tail end of the distribution, right? And you remove all those records, right? Essentially, you'll be losing a lot of information that actually is important, right? The example that Shahid gave, is important there. And when you drop them, it might not actually mean much for the distribution itself, but when you try to use that feature, in a regression, for example, and you use that feature as, say, a dependent variable, as an independent variable, then it starts to introduce a lot of bias downstream, even though it might not look like it had a negative effect on the variable itself, right?
And for the example that I did, missing at random, you saw that the higher values of y had a lot of missingness in x. So if you were to remove those, if you were to ever use in a linear regression, you would miss out on the higher end values of x itself. And so it would affect the information that's actually provided in the data set. And that is because it's missing at random and the way that it was missing at random. Your question is, I would say, accurate for missing completely at random, large data sets with small missingness. Yes, it makes sense to remove those missing values. You're not missing anything in terms of information, and also it's computationally more efficient than imputing.
How do you consider the relationships of different x variables? Like for sometimes, if you have a number of independent variables in your model, and they're kind of co-behave together, and because according to the mice imputation algorithm, if you're using that, it will basically looking for other numerical variables, and they're kind of making subgroups and imputing of the missing values. So I'm just curious, how do you consider the relationships of other x variables?
Yeah, so the question is, how do you consider the relationships of multiple different independent variables while imputing in our package?
So that's a great question. So the first point is that when you impute a variable, there's a difference between like an analysis model and an imputation model, right? So let's say your variable is y and you have x1 and x2, right? And ultimately you want to create a model, for y with x1 and x2 as independent variables, right? When x1 and x2 are being imputed, they actually become the target variable, and y and x2 impute x1, right? And then y and x1 impute x2, right? So for the imputation model itself, right? You're not looking at the relationship between x1 and x2, on y. But the second part of that is that like interactions between independent variables is extremely important. Right now, ours is just treating them all as independent, right? That's one thing that we want to work on, and essentially, that's a huge issue, right, in general, right? And you referenced the mice package, right? So that was like an inspiration for a lot of this, and that package actually goes into like multi-level modeling, interactions between terms, and how to handle that, right? So That's one thing we hope to get to. And if you'd like to help work on it,
Yeah.
submit a pull request.
But for now, I mean, I think Joe went over it in his multiple imputation, like complex example. We give you the option to use multiple independent to impute a single independent variable or vice versa. But that's kind of dependent on you understanding the interaction that's already there between your independent variables. And so that's, right now, that is where we're at right now.
All right, this is going to be a quick one.
So I'm just wondering if there's one variable that has a missing value, and there's a reason this variable has a missing value. But from looking at this variable versus the other variable, we couldn't tell what's the connection. But for me, it makes more sense to create a missing indicator. But how would this package solve that problem?
Do you want to repeat that?
Yeah, so if there was a,
Yeah, I think the one is, in what, like, why wouldn't you just create a missing indicator, right? And use the missing indicator as its own variable, right? Is that right? And again, I would say that similar to why wouldn't you just delete, right? There are places where that is appropriate. We didn't focus on like indicator variables in this case, but the short answer, and we can go into more detail, is that sometimes that also leads to bias if you use an indicator variable in like the wrong situations. There's actually a good passage about that in an article I can refer you to. That might be the best for now. So, but it's similar to the listwise delete example, right? In some cases that works completely fine. In other cases that leads to complications. Is the short answer.
All right, let's wrap this up. We're really just a little bit over time now. I really appreciate everybody coming today, and one more round of applause.